Okay, let's take a look at today's lesson. We're going to be looking at parametric equations today. So, parametric equations are a different way of describing things. Really, they're very good with describing movement. So, they're basically in two dimensions. We're in two dimensions. We will be moving into 3 dimensions in a bit. But in 2 dimensions, they're a pair of equations that express the coordinates x and y of points on the curve as separate functions of a common variable, the parameter. So let me just give you an example. So if we are looking at a scenario where a football is being kicked, okay, you've seen, in the past, like in Algebra 2, so you have this path, here's the ground, say there's a goalpost over here or something. You've seen that scenario like in Algebra 2 where you would use a parabola, right, an upside down parabola to basically explain or describe this movement. Instead of using parabolas, the equations that we've been using, those are in rectangular form. That's called a rectangular form or rectangular coordinates. So vocab words. Okay, rectangular form. So instead of going into rectangular form, there is another form. It's called parametric form. What we can do is we can describe this motion in terms of horizontal movement and vertical movement, all with respect to time. So if we're looking at this scenario, what we could do is we could write 2 equations, an x equal equation and a y equal equation. Okay, my x equal equation would describe this distance, some kind of a way to describe the distance from the kicker, f of t, and in this scenario we're setting x would be our f of t. X would be the f of t equation. We could just, make something up like 3t plus 1. That might be my equation that describes this distance. See how it's in terms of x, but, it's in terms of t, but it's x equals. So that's my horizontal movement. My vertical movement is the distance above the ground, so that's a vertical distance. And this particular scenario is calling it g of t, so y would be g of t. So, I don't know, y could be 2t minus 1, I don't know, or plus 1. I'm just making something up, or I'm just showing you what it would be. Parametric equations come in a pair. There are 2 of them. One describing the horizontal movement and one describing the vertical movement. Notice they're both in terms of t. So what we've basically done is we have introduced another variable t. It's called the parameter. That's where parametric equations gets the name from. That's a parameter. Now, does our parameter have to be time? No. In multivariable calculus we look at different kinds of parameters, but for Precal and Cal 1 and Cal 2, a parameter is typically time. That's our parameter. We're looking at real life situations where time is a factor. And so these kinds of equations will help us describe motion a little bit better, or a little bit more flexibility. Okay, so that is a parametric equation. So we have 2, an x equation and a y equation. These are called parametric curves. Even if it's a line, they're still called parametric curves. That's just what they're called. Where t is our parameter and I is our parametric or parameter interval. Okay, so that's kind of the new type of equation we're looking at today, is parametric equations. What we're going to practice a couple different things: how to graph them and how to eliminate the parameter. So the parameter t sometimes can be eliminated, and what it produces is basically a rectangular equation. It produces a rectangular equation. When we eliminate the parameter, we get a rectangular equation. We get something with just x and y in it. If we get rid of the t, think about this set of equations. If there was a way for us to get rid of the t, I would just be left with x's and y's, right? And that's a rectangular equation. Okay? If we have equations, parameter equations, that involve sine and cosine, and typically they would be sine of t and cosine of t, but sine and cosine, like this. This is what we would do. We would use our old friend Pythag. You probably missed him. I know it's been a while, like a day since we've had to mess with him. So that is something we're going to be using when we're working with parametrics that involve sine and cosine. Okay, so that's the topic that we're looking at today is parametric equations. So what we're going to do today is we're going to learn how to eliminate the parameter, and we're going to also learn how to graph them. Okay, any questions so far? All right, so let's go to the next slide. We have a couple of examples. So we're going to look at eliminating the parameter. We're going to work on that first. What do we do? So we have we have a set of parametric equations. We have an x equal and a y equal equation, and we want to get rid of the t. So we have a couple of choices. Really, substitution is typically what we do. I'm just going to say to eliminate the parameter with these circumstances, it is normal to use substitution. So I want to look at each one of those, the x equation and a y equation, and determine which equation we are going to sub for. So I adjusted your notes, right? So this is I cut the lesson in half. This is the half of the notes. This one was not on your slide, so you need to write this down. Okay, this second example was on the slide, but the first one was not. So if you would add that in. So we are looking at practicing eliminating the parameter. Okay, so what I'm going to do, I'm going to choose to work on the y equal equation and solve that for t. I think that would be easier. Do I have to? Well, I don't know. It would be really hard to solve the other one for t, wouldn't it? Just to get the t completely by itself? Because I have a t squared and a minus 3t. Could we do it? I mean, probably, maybe, but I mean, that seems pretty hard. Why do that? So let's just work on the y equal equation. Let's solve this for t. So I'm going to get t equals y plus 1. Now what I'm going to do is I'm going to substitute that y plus 1 into the x equal equation in place of the t. I want to get rid of the t, right? What I'm trying to do is eliminate the parameter. In other words, get rid of the t's. So let's go put it in here. So I have x equals, and then I have y plus 1 squared minus 3 times y plus 1. Okay, so we're going to hold there for a second. So all I did is a substitution. Are we okay with that? Now I can't leave it like that. What I have to do is I have to put it in terms, what would my rectangular equation look like? Because I'm going to have to identify what this curve is. What would it look like? Well, it really wouldn't typically look like that. We don't have an x equal with all that craziness over there, right? So we're going to FOIL and distribute combine like terms. We're just going to do some algebra to get it to in its proper form. So let's see, what would that be? Y squared plus 2y plus 1. Now I'm going to distribute the negative 3. So negative 3y minus 3. So now let's combine like terms. We get x equals y squared minus y minus 2. Okay, so that looks more normal. What would that be? If you think back to your Algebra 2 days, what is that equation of? It's a parabola, right? It's a sideways parabola, isn't it? This is a parabola that opens which way? Does it open right or left? It opens right. So we're going to describe, and I'll just add the instructions down here, describe the curve. We're going to describe the curve. What that means is say what kind of rectangular equation it is. That's all. Describe the curve. This is a parabola, and it opens right. That's my description of the curve. Parabola opens right. Here is my rectangular equation where I have eliminated the t. The t is gone. Okay, yes. Yes, it depends on really what we want our guidance to be is what would it have looked like in regular form in our previous work. This would have been, actually we probably would have, completed the square and done stuff to it, but we don't need to. This would have been just a standard form for a parabola that opened right. Right? So yeah, you just want to put it in, just kind of recognize what does this look like that I've seen before. I'm not going to give you anything that you have never seen before. It'll be something that you've already worked with or graphed. Okay, so that's an example of how to eliminate the parameter with x's and y's and t's. Are we okay with that? Okay, so what we're going to do now, we're still going to work on eliminating the parameter. We're also going to learn how to graph. we need to know how to graph parametric equations. They're graphed a bit differently than our rectangular equations because they show motion. They have a beginning and an end. They show motion. So let's work on this one. So what I want to do is a t-chart. Yay, a t-chart, right? And oh, it's a triple t-chart. I mean, who wouldn't want to do a triple one, right? Just a boring 2 one, that's just boring. So we're going to do a triple t-chart. Who knew that this excitement awaited you today? So we're doing a triple t-chart. And we are using, this is our time. We're going from 0 to 2 pi. And I'm just going to work with the quadrantals. You know, can you do other values? Sure. Do as many as you want. But I think we'll get a fairly good picture if I just work with like 0, pi over 2, pi, 3 pi over 2, and 2 pi. I think that gives me a good enough picture. I don't need any more values than that. So let's generate our t-chart. How do we do that? Well, we're going to take our t value and we're going to put it in the equation for x. We're just going to put it over here. So if I substitute, if sine of 0, we know sine of 0 is 0. 0 times 4 is 0. So my x coordinate at time 0 is 0. Now let's get our y coordinate. Let's put it in here. When cosine is 0, that's 1. Right, 1 times 4 is 4, so there's my first point, 0, 4. I'm going to go ahead and collect all of the points before I graph it, just so we have a, so it kind of flows a little bit better. So let's work on pi over 2. My x value at pi over 2, sine of pi over 2 is 1, so 1 times 4 is 4. Cosine of pi over 2 is 0, so we're 0. Okay, let's go to pi. So sine of pi is, 0. Cosine of pi, though, is a -1, so that would give me a -4. We doing okay? So 3 pi over 4, sine at 3 pi over 4 is -1, so that would be what, -4. Cosine at 3 pi over 2 is, 0. And sine at 2, so we're back to the start, right? We're back at 0, 4. So what this wants us to do is describe the direction of the curve using arrows. So when we graph, we're going to use arrows. And we're going to note the exact starting and ending points with ordered pairs. Okay, so my time starts at 0. My first point is at 0, 4. So I'm going to do what that said. I'm going to write the point there, 0, 4, and that's my start. It's my start point. Okay, so at time 0, that's where we are. Now let's look what happens when we go to pi over 2. Then our point is 4, 0. Right here. Now we want to connect these points with a curve, not with a straight line when it's like this, when it's sine or cosine, something like that. And the curve really should kind of go out. It should kind of go out. Think out whenever you're doing a curve instead of in. Okay, so which direction am I going? I am going this direction. So I need an arrow there. Just one arrow is fine. You can put, I don't know, I've seen students put, I don't know if they could even put any more arrows on there. They put so many arrows. I mean, it almost looked like a little porcupine. I mean, I don't know. You can put as many arrows on there as you want. I mean, really 1 or 2 is sufficient, but we just need to know which direction we're going. Alright, so then that pi at time 3.14, we're at 0, -4. So we're down here, so we keep moving around this way. You can put another arrow if you like. You don't have to. Then our next stop, let's see, we are at -4, 0. Okay, we go this way. And then we're back to, actually our starting and ending place is the end. We start and end at 0, 4. Now, I know this isn't a great graph, but if this were more, symmetric looking, what would that be a graph of? It would be a circle, right? It would be a circle. So that we think it's a circle. We're pretty sure it's a circle. What we're going to do is we're going to eliminate the parameter and we're going to say, what it is. We're going to describe the shape of the curve. So we eliminated the parameter here by substituting. That technique really does not work well for cosine and sine. Really does not work well. I'm going to show you a different technique. So if it looks like this, x equals, so and so, what we're going to do is we're going to square both sides. So I'm going to get x squared equals 16 sine squared and y squared equals 16 cosine squared. Okay, that's my first step, is to square both sides. If you like to write steps, you should write that down. We're squaring both sides. Okay, so once we square both sides, we're going to add those two equations together. We can add any equations we want. We just need to, the equal signs need to line up so that we're not traveling across equal signs. So this is going to be x squared plus y squared equals 16 sine squared plus 16 cosine squared. Do we see that lining up for something that we like? It's one of our little favorite guys, right? So can't I factor 16 out of the right side? That's a thing, right? I can factor. So x squared plus y squared equals 16 times sine squared t plus cosine squared t. What do we know sine squared t plus cosine squared t is? It is 1. And 1 times 16 is 16. So we have x squared plus y squared equals 16. Much more recognizable, right? We recognize what that is. That is a circle of radius 4, which is exactly what we drew. Right? So this is rectangular form for a circle of radius 4. This right here, that's my rectangular form. This is parametric form for a circle of radius 4. Now, I just want to point something out real quick. So notice how here, let's talk about the parametric form. I think we're good with the circle form. In fact, let's just finish that part off. That's a circle. Okay, we described the curve. It's a circle. I do want to talk a little bit more about this parametric form. Notice that the x and the sine are paired up. Is that normal in trig? No. It's not normal, is it? And the y and the cosine are paired up. That's not normal. Is this movement normal in trig? Do we usually go this way? Do we usually start at the north line? No. We usually go this way? No. So what do you think would happen if I put these in the way like x equals 4 cosine and y equals 4 sine? What do you think would happen? It would start, yeah, and it would go the opposite way, counterclockwise. So that does make a difference on how these are paired up. It's not just any circle of radius 4, it's a special circle of radius 4 going a particular direction and starting in a particular place. Right? So that's the difference between parametrics and rectangular equations, is we have more. There's more for us to work with on a parametric equation. Does that make sense? Are we okay with that? So I could make a completely different problem if I mix these up and put the y with the sine and the x with the cosine, and maybe change the change the time up some. I mean, I could make like part of a circle, or I mean, there's a lot of variety that we could do here. Are we okay with this one? Okay, so last one for today. Let's look at this. You see the sine and cosine, and you're thinking, well, I wouldn't really recommend squaring both sides at this point. There is a different way to work this one. But before we go through that and, doing our eliminating the parameter, let's graph it first, get a feel for what's happening. So yes, we get to do another t-chart. Yay, a triple t-chart. Ooh, triple t-chart. So let's put it here. T, X, Y. We start at 0. And we go to 3 pi over 2. So let's do 0, pi over 2, pi, and 3 pi over 2. Let's do those. Are we getting a good idea of how to do the t-chart? Are we okay with that? I'm going to take the 0 and I'm going to sub it up here into each of these locations. So cosine of 0 is 1, so my x-coordinate would be 5. Right, and sine of 0 is 0, so my y-coordinate is a -3. Is that okay? So we do pi over 2, cosine of pi over 2 is 0, so my x would be 2. Sine of pi over 2 is 1, so I'd have a -8. Pi, let's see, cosine of pi is -1, so what would I have? I'd have a -1 here. Check my arithmetic. Are we okay with that? Cosine's negative and sine of pi is 0, so it'd be a -3. Cosine of 3 pi over 2 is 0, so that's a 2. Sine of 3 pi over 2 is -1, so that's a 2. Okay, do my points look fine? -3, -8. Yeah, we're good to go. Okay, so let's graph it. Okay, 1, 2, 3. Looks like I need to go down to -8. So we'll just extend that a little bit. Okay, so our first point is at 5, -3. Oops. Puts this here, and I'm going to start. So this is the start, and it's at 5, -3. Okay, so I plot my first point, I write start, and I label the value of the point. Okay. So let's plot our second point. Our second point is at 2, -8. So down here, I'm going to connect those together with the curve. We want to curve out, not in. So, okay, my arrows are going that way. Okay. My next point is at 1, -3. Right here. Alright, so we curve back up this way. And my last point is at 2, 2. And this would be our end, and that's 2, 2. Okay, what does that look like? It's close. Which? That's an ellipse, isn't it? Is it a complete one? No. It's like a partial ellipse. That's a partial. So that's what we're gonna. This is a partial ellipse. We're describing the curve. Now let's eliminate the parameter. Let's see what kind of equation we get. All right, yay! So now here we're going to do something similar to what we did with the circle. It's similar, but it's not quite the same. What I want to do is I want to solve for sine and cosine first before I square both sides. I'm still going to square both sides, but I want to solve for sine and cosine first. So let's work on cosine. So let's see, that would be x minus 2 divided by 3 equals cosine. Right? I'm solving for cosine. I move the 2 over, divided by 3. Now I'm going to square both sides. So I have x minus 2 squared over 9 equals cosine squared. We okay with that? Now let's work on the sine equation. So I'm going to move the 3 over. So y plus 3 divided by -5 equals sine. Now I'm going to square both sides there. So I'm going to get y plus 3 squared over 25 equals sine squared. Okay, what do you think I'm going to do now? I'm going to add those two equations together, right? Being sure to keep the left part on the left side, right part on the right side. So I'm going to get x minus 2 squared over 9 plus y plus 3 squared over 25 equals cosine squared t plus sine squared t. And we know what cosine squared t plus sine squared t is, right? It's 1. And what does that look like? That looks like a rectangular ellipse equation, right? Ones that we're familiar with. That's exactly what that is. So my equation would be x minus 2 squared over 9 plus y plus 3 squared over 25 equals 1. So that's what an ellipse looks like in rectangular form. This is what an ellipse looks like in parametric form. Okay, what do you think would happen if I switch the x and the y? I put the y with the cosine and the x with the sine. Would I get the same exact thing? No, I wouldn't, would I? What would change? What do you think would change? It would move a little bit. It would also be, there'd be a direction. Would I be going left like this? Would I be going counterclockwise, do you think? No, I'd probably be going clockwise. So we really just need to be aware of that any slight change we make can change the whole dynamic of the parametric equation. Mm-hmm. Okay, true. So that's a good question. From the rectangular equation, is there a way for me to know that this isn't a complete ellipse? What we would have to do is we would have to restrict this domain in some way. We have to restrict it. Now, I'm not going to make you figure out what the restriction is. Okay? But I don't know, we would have to leave this part out. So what would we restrict? I don't know, it's not a function. That would be kind of hard, right? Because we can't really restrict the y covered and the x's are covered. So that would be kind of hard to restrict this in order to say it's partial. Maybe not even possible to do. But in parametrics it is. It's possible, right? We just stopped the time. We went from 0 to 3 pi over 2. How far do you think we would need to take the time to complete the ellipse? To 2 pi, right? 0 to 2 pi, that should complete the ellipse for us. Okay, so the parametrics help us indicate that it's just part of an ellipse. Okay, anything else? Okay.